question 5 kind of extends also into question 6. It says, find the coordinates of the foot of the perpendicular from the point 4, 5, 6 to that plane. So the foot of the perpendicular means where it is perpendicular on the plane, so where it touches. So again, it's kind of hard to draw, but if that's your plane, then your perpendicular, this would be the foot of it. Okay, so you call that P, and it says from this point. So we'll call that close. So meets the plane at 90 degrees. So think about that. Really what you're trying to find is where the intersection of that line is with the plane, the point of intersection. Well, this line, if it's perpendicular, has a direction vector that is the normal to the plane. And then it passes through a point. So for an equation of a line, you need a point and a direction vector. So the perpendicular line could have the equation passing through that point 5, 4, 5, 6 with direction vector the same as the normal. So this has a normal of 1, 2, negative 2. So that's actually the line going all the way through. Okay, and we want to know where it intersects. So actually a nice way to draw something like that is to do it dotted. Okay, so you can see it there, then it's dotted because it's actually sort of underneath the plane and then it continues. So, intersection of a line and a plane. You have the plane in Cartesian form. This is in vector form. If you find the parametric form, then you can substitute all of the x, y, and z components into the Cartesian form and solve for t. Because remember that t value has to be the same for every component. So that will be 4 plus t plus 2 times 5 plus 2t minus 2 times 6 minus 2t equals 9. so then you can just go right to P. So remember, you're substituting 7/9, so 4 plus 7/9, 36 plus 7 is 43/9. But if you need to do it on the side, you can do it. Okay, so then 45 plus 14 is 59. And then 54 minus 14. So that's the foot of the perpendicular. If you take a look at the next question, it asks you to find the closest distance, or perpendicular distance, which is the closest distance from a point to a plane, which means we've kind of done one part of that. Two methods of doing it. But if you know where that closest point is to the plane, then you just need to find that distance. Okay? So the magnitude of the vector, we call that upper point Q, PQ. So that's the first method that we're going to use, using the coordinates of the foot of the perpendicular and point P from example 5. So actually, we call P the other point. So in any case, so this is called P here. So we want to find, so let Q be foot of the perpendicular. So different from the diagram. So that is, what was that, 40, 49, 43, 59, 40. Okay, so therefore, PQ is that vector really gets you back to the component one, but anyway, that is going to be so 7/9, and then 14/9, and then negative 14. No. Yeah, negative. So 7 squared plus 2 times 15 squared. And we got simplify for 41. Yeah. Oh, it goes exactly. Oh. Okay, so then another method. Okay, using the dot product and the definition of cosine. So I'm going to draw my diagram again here. So we know a normal, right? We have this point here, we have this point here. So now we're calling this P and Q. And we want to know that distance. If I were to draw another vector from P, because remember, if we know the equation of the plane, we can get any point on the plane. We just don't, without doing that first step that we did in the previous question, we don't know what the closest distance is. We could get any point, though, very easily, right? So let's say we get another point here and join it up with point P. So that you could do. This vector, okay, let's call it vector W, let's say. It's something that you could easily come up with. If you think about that drawing then, remember this meets at 90 degrees. So I'm going to actually draw it 90 degrees so that it forms a 90-degree triangle that way. Okay, if we think about this diagram, this distance that we want is really the projection of W onto the normal vector. The normal vector keeps on going, right? You don't know the magnitude of it. But that is a projection onto the normal vector. So really what we're wanting to find here, so magnitude of PQ is the projection of W onto the normal vector. Okay. So, in comparing, so if we have the normal and we come up with vector W, we could call that angle between them theta, right? So so PQ, if we think about cosine of theta is adjacent over hypotenuse. So cosine theta is adjacent over hypotenuse. Okay. So we could rearrange that to find PQ. Problem is, we don't know what the angle is in between, right? But remember, with dot product, or scalar product, or whatever you want to call that, there's a relationship between theta. So if we have, what vectors do we know? We have the normal and the vector W. We can find that point, any point on the plane, and we can find vector W. So think about if I did the normal dot product with W, definition of dot product. Sorry. Okay. So let's solve for cosine theta, and then we don't have to worry about what angles in between. Right, just like how you would calculate the angle in between any vectors. So therefore, these are equal. And so really, when you look at this and solve for PQ, multiply through by magnitude of W, divide out. Okay. So we know the normal, and we can find W. So we went through, this is sort of the theoretical part of it, but now we're actually going to do it. So find any point and choose nice numbers. Like, please try not to get too many fractions. Like, the zeros are good. So maybe you want to, there's the equation of the plane. So how about zeros for y and z? X is 9, right? Rather than fractions. So how let y equals 0, z equals 0, therefore x equals 9. So what point do you want to call this? T. T is 9, 0, 0. Okay, that's a point. So therefore W is equal to ET, and that's going to be 900 minus, what was that, 0.456? So 5 minus 10 is negative 5, plus 12 is 7, 1 plus 4 plus 4 is 9, root of 9 is 3. Okay, this should be the magnitude. Okay, so if you're ever asked for the closest distance from a point to a plane, you can do it by finding the intersection, then calculating the distance, or a little bit faster is the normal vector, dot product with a vector formed from the point to any point on the plane, because that's easy to find, divided by the magnitude. Okay, so that's helpful. Okay. All right, take a look at the next one, acute angle between that line and the plane. So remember, you need a direction vector, right, between, if it's two lines, you need both direction vectors. Now we've got a line and a plane, so where they intersect, you need a direction vector of your line and any direction vector on your plane. Okay, so take a look at the equation of the line. It's in Cartesian form, so come up with the direction vector first, or put it into vector form, do the whole thing if you want. That makes it easier. here, all of the x, y's, and z's were positive. All right, so there's no rearranging. This is like over 1. So really the denominators will be your direction vector, as long as it's x equals, or sorry, x minus or plus equals y minus or plus. If it's switched around, so say that last one was 5 minus z, rearrange it so that there's negative 1s in the denominator. Okay. So let's draw a little diagram again of your plane. Got a line going up. So here, line, and then, okay, so it looks something like that. You want the angle between that line and the plane. So if I draw a direction vector here, this is the angle I want. Okay, I don't really know what the orientation is. I don't really know what the orientation is of the line. Okay, but that I want either the acute angle. In this case, I did say acute angle, or you might, by your calculations, depending on which direction your direction vector is, if it's positive or negative, it might give you the obtuse angle. Okay? Now, we would have to then, if we were comparing that to an angle on the plane, we'd have to come up with 2 points on the plane, find that vector, right? And then do it. Totally fine. But what do we know about a Cartesian equation of a plane? Is we know the normal, right? So here's my line here. So if I'm looking at this straight on to a plane, so here's my plane, and here's my line touching the plane, and then continuing through, and I want this angle here, okay? I'm looking straight onto the plane. I know this normal here, so that's like a direction vector. I know this direction vector. If I find this angle, I want this one, what do I do? Subtract from 90, right? Because the normal meets the plane at 90 degrees. So that's the fastest way, okay, is to calculate the angle between the normal and the line, and then subtract from 90. So calculate the angle between the normal and the plane. Okay, so we've got our direction vector here. Our normal is 1, -1, 1. Okay, so cosine theta is going to be dot product divided by magnitude. You can just do that. So 4, 6 is 21, 3. Okay, move. So second, you'll notice it's a negative here. Okay, so we get here, we get 97 point, I didn't say what's around. I'll go to 1 decimal place. Okay, 97.2. So that means the angle that is with the normal to the line. So there's the normal So the line, say, is on your right there, a little bit more, okay? So we want to then get this angle, the acute angle from there, and then subtract that from that. Okay. So acute angle and then, therefore, angle, kind of wrote a little bit too big here, sorry. Is 90 minus that. Which is 7. So very close to the really close. Now, depending on what direction, like if you had changed the direction vector, remember here, you could have -2, -4, -1 going the other way. You could have 4, 8, 2, negative those. If you had changed to the opposite direction, then you would have got 82.8 right away, and then you just subtract. Now I put a diagram on there for the next one so that helps you visualize a little bit. Okay, so what you can see here, if we're looking for the angle between the planes, then at some place they are intersecting. Obviously, if they're parallel planes, remember they intersect. So two intersecting planes, we want the angle in between them, theta. Okay, what can we do? We do know right away what the normal vectors are to each one. So there's N1 for the bottom plane, N2 there. These intersect, okay, and this angle here is the same as this angle here. How does that work? Well, if you were to join, think about, you join this up here, so you make a quadrilateral there that is equal, sorry, I'm not doing a very good job on this one. Okay. So, thinking about this, if you divide that, well, this angle here actually, before I do that, this one's 180 minus theta, okay? These angles here are 90 degrees, right? Any vector on the plane with the normal meets at 90. So if I'm just joining this up, a vector on this plane and the vector here, those meet at 90. Quadrilateral has angles that add up to 360, so that means these two have to add up to 180. Well, if this is 180 minus theta, right, then this would have to be theta in here. So this angle is the same as this one. Okay, so that they add to 180. So if we find the angle between the two normals, that's going to be the same as this angle between the two points, based on properties of angles and polygons. So your normal here, 1, 2, -1, got normal 1, normal 2, 2, -5, -4. Okay. And find the angle between those normals. And again, here it didn't say acute or obtuse, so there's going to be two. They intersect in we're talking two planes. You're going to have one angle that's acute, this one, and one that's obtuse. Okay? So, it doesn't specify here, so either one I would accept. If I say acute, then you have to make sure that you get acute. So here our answer is. And again, anytime you have a negative in the numerator, you know you're going to get an obtuse angle. Because remember, angles bigger than 90 are in the second quadrant when you are grabbing them on the unit circle, and cosine is negative in the second quadrant. See how important math 30 is? And again, I didn't say what to round to, so we'll go to 1 decimal place. Work on practice questions, continuing on from my section from yesterday.